So in this lecture, we're going to discuss the first two experiments of the four Stern-Gerlach experiments we use to kind of highlight the weirdness that is involved in quantum mechanics. And we're going to analyze these and look at them using what we discussed last lecture, the concept of state vectors to describe quantum systems and how we determine the probabilities of given measurement outcomes. If you remember, the first experiment we looked at had essentially just our beam of particles, or spin 1/2 particles, coming out of our oven and into the first Stern-Gerlach analyzer to perform that state preparation we had. And all the output states of that analyzer from the spin-up state went into a second Stern-Gerlach analyzer that measured that spin component in the z direction. And what we saw was all of the particles that went into that final Stern-Gerlach experiment were measured as spin up. This seemed kind of obvious. This was kind of what we would have expected. Classically, you measure something and then you remeasure it, you get the same result. But just for the sake of going through what we learned last time, if we wanted to calculate this, we would say the probability of measuring a spin up state was equal to the projection of our input state, which is, this one, going into that Stern-Gerlach analyzer onto the measurement result squared. And since we know that those two, that inner product is equal to 1 squared gives us 1, and the probability that we measure the spin up state is 100%. All of our input states are up, are measured as spin up. Nothing really huge there. If we were going to do the probability that we measured the spin down state, we would do the same thing, but we would be projecting onto the spin down state our current state plus, and that gives us 0, and we can see that none of our measured states are in the 0 state, so this gives us exactly what we see. Now our second experiment is a little bit harder to analyze with the tools we've got so far. We had essentially, the same setup where we had our beam of spin 1/2 particles going into a Stern-Gerlach analyzer aligned in the z direction for state preparation. All the spin up in the z direction beams coming out of that, all the measured particles that were measured as spin up, are our input state into a second Stern-Gerlach analyzer aligned in the x direction. And what we saw is that 50% of the particles that went into that x Stern-Gerlach analyzer were measured as spin up in the x direction, and 50% of them were measured as spin down in the x direction. So just to write that out, what that looks like is the probability of measuring a spin up in the x direction was equal to 1/2, and the probability of measuring a spin down in the x direction was 1/2. And that was both with the input state of spin up in the z direction. So if we want to calculate one of those, we have spin up in the x is just going to be the projection of our input state, that spin up in the z direction, into the measured state, spin up in the x direction, squared, right? But, and likewise, for the spin down in the x direction, this is going to be equal to the projection into the spin down in the x direction state of our input state, spin up. The problem is we don't know what these state vectors are. We don't know what a spin up in the x direction state looks like, or the spin down in the x direction state. But what we do know is that any state in our Hilbert space can be described as a linear combination of our basis vectors, the spin up and the spin down in the z direction state. So that means, this is just in general, so that means for our spin up in the x direction, there is some coefficient a and some coefficient b such that this is true. Likewise, for spin down in the x direction, there is going to be some coefficients that make this true, because I can write any vector in my Hilbert space as a linear combination of my spin up and spin down in the z direction states. They form a basis. So now we can just take these two, if we want to get the bras for those, that's just going to be the complex conjugates of those coefficients. like that, we can take that and we can plug that into how we calculate for our probabilities and try to sort this out, right? So if we want the probability of measuring a spin up in the x direction, we know that that's going to be equal to, I'm going to do this inside brackets, plus a minus complex conjugate of b dotted into, or the inner product of that with our spin up all squared. Since the plus and the plus, the spin up states are normalized to 1, the spin down state and the spin up state are orthogonal, so this is going to be 0. We end up with just the magnitude of a squared, right? Likewise, if I wanted to look at the spin down state, I'm going to end up with this. I'm being kind of inconsistent here with the side that I'm putting my coefficients on. Again, these are just complex numbers, so you can put them on either side. But if we do this for the spin down in the x direction state, again, we're just going to end up with the magnitude of c squared, because this is going to be the plus and the plus equal 1, the minus and the plus equal 0. We get that. And if we wanted to look at the probability of measuring the spin, if this was the input state, we'd get the same thing with 1/2, 1/2. And we basically just showed that the magnitude of all of these coefficients are going to be 1/2. So we have a squared is equal to b squared is equal to c squared is equal to d squared is equal to 1/2. We're we're not done yet, though. What that tells us is that these complex numbers have a magnitude of 1 over root 2, right? So we still don't know everything about what we need to about those state vectors. So one of the things we can do, so uh, we know that a squared or any of those coefficients is 1/2, or the magnitude of a is equal to 1 over root 2. Now that a, b, c, and d, those coefficients are all complex numbers. And if you recall, any complex number z can be written as some magnitude e to the I and some phase, right? So what we've just shown is that the magnitude of all of those coefficients are 1 over root 2, but we still know nothing of the phase. So if we go back to our spin up in the x direction, which was a spin up plus b minus, these can all be written as, I can factor out that 1 over root 2 and just write e to the I, we'll call this theta, plus, and we'll call this one e to the I phi minus, right? We need to figure out those phases. Now, it turns out that let's just factor it out, and we'll get to why in a minute. But let's factor out this e to the I phi, e to the I theta, and we get 1 over root 2 e to the I theta times spin up in the z direction plus e to the I phi minus theta spin down. And we can rewrite that just as 1 over root 2 e to the I theta plus e to the I, and we'll call this alpha. Turns out this phase factor, we call that a global phase, doesn't matter. It has no physical meaning. And we can get into more detail in that later, but what we're really concerned about in these state vectors is the relative phase, what this alpha is. So we're gonna try and figure that out. The other thing, if we were to have done this same thing for this spin down in the x direction, we would have gotten the same thing and been able to write this 1 over root 2 e to the I, just so they're different, theta prime, plus e to the I, we'll call this relative phase beta. But we've got these two sort of equations for our state vectors. We're going to get rid of this global phase and end up with just our two vectors, 1 over root 2 plus e to the I alpha minus for our spin up in the x direction, and our spin down in the x direction is 1 over root 2 plus e to the I beta minus. And now everything we want to know, we're going to have to figure out what these relative phases are for these two state vectors. Unfortunately, to figure those out, we need some more information. We've used everything we have from those measurements we made. The last thing we need to do is we could set up another experiment to show this, but hopefully you can follow along and see from just by mapping what we did in the z direction to the x direction, these two states are actually orthogonal. The spin up in the x direction and the spin down in the x direction are orthogonal. So what we know is that that is going to be equal to 0, right? And this is what we're going to use to be able to figure out what those relative phases are. If we wanted to do a measurement to kind of show this, we would have just taken an output from a Stern-Gerlach analyzer in the x direction and feed it into an input of a Stern-Gerlach analyzer in the x direction. We would have seen, the same sort of thing we saw in Z. But if we want to calculate this, we can just take that inner product, and what we get is we're going to get the 1 over root 2 times plus e to the minus I alpha minus, and that's going to be dotted into 1 over 2 plus e to the I beta. And if we do this, multiply it through and all that, this is going to be 1 over root 2. Let's just get that out. This is going to be plus and plus. Then we're going to have e to the I beta plus minus. Then we're going to have plus e to the minus I alpha plus, and plus e to the I beta minus alpha minus. This ends up being equal to the 1/2 can just go over the 0. We're left with that. So we end up with, plus e to the I beta minus alpha minus, or 1 plus e to the I beta minus alpha. And this all equals 0 because they're orthogonal. So what do we get? Let's just do a little more algebra. We get -1 is equal to e to the I beta minus alpha. Negative e to the I alpha is equal to e to the I beta. And we have this relationship between our relative phases. Fortunately, that's not enough to really tell us which is which. Turns out what we have a little freedom here. If you can imagine, if we go back to our spatial coordinate system, x, y, and z, if you choose some z direction, you have the freedom then to choose which direction the x direction is anywhere in that xy plane. So we're able to sort of, similar to that, we're able to choose whichever one of these, set one of these to whatever we want. And the convention normally is to set alpha equal to 0, which means -1 is equal to e to the I beta, which means beta is equal to pi. And if we do all of this, that means our basis vectors, or sorry, not our basis vectors, our spin up vector in the x direction can now be written as the spin up in the z direction plus the spin down in the z direction all over root 2. And likewise, if we do the same thing, we get the spin down in the x direction is, is this, where we have the spin up minus spin down over root 2, and then for the spin up in the x direction case, we have spin up plus spin down over root 2. Where again, this is all still relatively new for all of you, but these plus and minus, the spin up and spin down, are in the z direction, whereas this is the spin up in the x direction. And we've figured out what our spin up and spin down states in the x direction are, written in terms of our spin up and spin down in the z direction, our basis states. Turns out that these two vectors also form a basis. So I can also write any general vector in my Hilbert space as a linear combination of the spin up in the x direction and the spin down in the y direction. And I will likely assign a homework that has you showing this as one of the problems. Anyway, that's where we're going to stop for today's video. Next video, we'll discuss sort of following along with the book. We're going to discuss what these states are. They're actually what we call superposition states, and we'll discuss what that means.